Okay, the next chapter is trees. And here what we will be discussing is not about the natural trees, but here we'll be discussing how the data internally in computer system is structured in a way that is just similar to the way it can be expressed in the form of tree structure. So the terminology tree is inherited because here in a computer system the data items stored in the computer memory. When we just visualize the connection between the data items in a computer system is just almost closest to the structure of a natural tree. That's why we inherited that's why the terminology tree is inherited and used to describe, to represent this concept, this structure, way of structuring data items in a computer memory. So this representation is used. So tree, when we define a tree in this context, tree is a set of nodes and edges that connect pairs of nodes So the nodes or data items are connected with each other. So that connection, the structure that is formed due to that interconnection of nodes is termed as tree. So it is an abstract model of the hierarchical structure, and there are different types or categories of trees, and a rooted tree that is the one having one node distinguished as a root. So we may have a non-rooted tree, but in a rooted tree, one node is just distinguished as a root of the tree. That is the node from which the connection or the structure or the interconnection of the nodes starts. Every node C except the root is connected from exactly other node P, and P is C's parent and C is one of the C's children. So every node except the root, except the root node, every node is connected from exactly other parent node. So if it is connected from the other node, and that node we call the parent node, and the nodes that are connected to that particular node we call them the children nodes. So there is a unique path from the root to each node, and the number of edges in the path, we call it the length of the path. For example, if this is the structure of the nodes, so those nodes are nothing but data items. For example, if we created data items of students, so like their ID, their gender, their department, or their section. So each node will represent each student. So represent corresponds to each student data set. So each student will be represented as a node, and one node from which the connection started will be considered as the root. So assume we have a structure, a tree structure like this one, a rooted tree. So the root node is A. Root node. The root node is A. So this a root node, because why it is considered as a root node is because others are just connected to that node, and other nodes like B, E, F, and G, they are connected to A. So those are the children of A. Children of A. And this is the first node of the tree, which is the root node, and it is the parent. So without the without parent, the root is without parent. Root node is always the one without parent. Without parent. Internal nodes. Internal nodes. A node with at least one child. A node with at least one child. So from these three, we can consider A as internal node. The root node itself can be considered as an internal node, because an internal node is the one which is with at least one child. So here A is having 4 children, so we can consider it as an internal node. B is an internal node because having 2 children. E, not an internal node because there is no any node below E. F is an internal node because contains H, I, and J. So are children, the first children of F. I is also an internal node. J is also an internal node. J is an internal node. And external or leaf nodes, a node without a child. A node without child. So we can consider C, D, E, H, K, L, M, and G. Those are the internal nodes because they do not have any child. Ancestors of a node. Parent, grandparent, grandparent, and it is of a node. So ancestors of a node. So we just consider, for example, K. We can consider K, and ancestors of K are the parent, which is I, and the grandparent, which is F, grandparent, which is A. Similarly, for M, ancestors of M, the parent is J, grandparent is F, grandparent is A. So these are an ancestors of node M. So ancestors, we just start from the ancestors of a node. We just start moving from that node and moving towards the root. So and considering the parent and grandparent, grandparent, and until we reach at the root node of the tree. Descendants of a node. Just this is the children, grandchildren, grandchildren, etc. of a node. That means we start from the from that node and continue moving down to the terminal nodes that are descended from that particular node. So, for example, descendants of F, for example, descendants of F, H, I, J, then K, L, and M. Those all are the descendants of F. Descendants of F. The debits of a node are just the number of ancestors or the length of the path from the root node, root to the node. So here the debits of h is 2. The debits of h is 2 because the number of ancestors are the number of ancestors is 2. That is, there are two ancestors, A and F. The length of K, it is 3. I, F and A, or A, F and I, or the number of ages 1, 2, 3. So this 3, the length of K. The height of tree. The height of tree is the depth of the deepest node. The depth of the deepest node. For example, the height of the tree is 3 because the deepest node, that means the node at the last deepest level of the tree. We consider the nodes at that node, and starting from those nodes we can start counting the number of edges upward up to the root node. So here the deepest nodes are K, L and M. So from one of those nodes we can start counting the number of edges. So 1, 2, 3, or 1, 2, 3, 1, 2, 3. So 3 is the height of the tree. Or for example, if we consider this subtree, let's consider this subtree. The height of this tree, is 2 because the deepest nodes are K, L and M. So from one of those nodes we can just count the number of edges until the root node. So for this small tree we have the root F and the internal nodes F, I, J, terminal nodes H, K, L and M, and the height of the tree is 2. So subtree is a tree consisting of a node and its descendants. That's why we considered F as for this node F. We can consider all the descendants of F, and together they form subtree because it is part of the largest tree or the biggest tree. So we can consider this one as a subtree. We can also consider this B as a subtree, B, C, D as subtree, or J, L and M subtree, one subtree, I and K, one subtree. So subtree is just a part of the tree, and considering one node and its descendants. Binary tree is a tree in which each node has at most two children. Called left and right. So in a binary tree, each node has at most the maximum number of children that can be added under a given node is 2. So here each node is having the maximum of 2 branches. So for example, can we consider this one as binary tree? No. Why? Because F is having 3 branches or 3 nodes. So because of the existence of this third branch, the tree is not binary tree. The maximum number of children is on the left side and on the right side. So maximum 2. Only one is possible. 0 without any child possible, but more than 2 is impossible in case of binary. Bi means 2. Full binary tree is a binary tree where each node has either 0 or 2 children. That means full binary. That means every node is either having 2 children under it, or no any child. So for example, if we take this one, this sub 3, this is not full binary tree. This is not a full binary tree. Why? Because for this to be a binary tree, it should be first a binary tree. For this one to be a full binary tree, first it should be a binary tree. This one is not a binary tree because there are 3 branches under F. So this is not a binary tree. But if we remove, for example, H, then it becomes binary tree. But it can not be considered as a full binary tree. Because why? Because here under J we have 2, but under I we have 1. Having 1 child is not allowed in full binary tree. So if we remove H and K from this subtree, this can be considered as full binary tree. And the other one is balanced binary tree. Here the binary tree where each node except the leaf nodes has left and right children, and all the leaves are at the same level. So if there is any child having nodes, it should contain the left and right nodes, and all terminal nodes or leaf nodes are at the same level, should be at the same level. So the simple structure of balanced binary tree is like this one. So left and right, then the terminal nodes are at the same level. Complete binary tree, a binary tree in which the length from the root to any leaf node is either H or H minus 1, where H is the height of the tree. The deepest level should also be filled from left to right. So for a given binary tree to be considered as a complete binary tree, the length of the tree or the height, the length of the root to any leaf node should be H or H minus 1. So we should first calculate the height and check if the length from the root to any terminal node is H or H minus 1. Complete binary tree. So it can be H. For example, if this one is 3, then 4, 5, 6, 7, 8, 9, let's say, or just 7, 1, 2, 3, 4, 5, 6, 7. So the height of this tree, can be considered as 2. Just the height is equal to 2, because the height from the number of edges from the root to the terminal node, the deepest terminal node is 2. 1, 2, 1, 2, 1, 2, 1, 2. So the deepest nodes are the 4 terminal nodes, are the deepest nodes. So from the one of those nodes we can just calculate the height of the tree. So the height of the tree is 2. So as all trees, all nodes from the root to the terminal nodes, the height is H. We can say it is complete binary tree. If we, for example, we remove 1, we just reduced the height of this this side can be H minus 1. The height to any terminal node, So if we remove, for example, this one, if this one is also removed, the height of the tree becomes, the length of this node is 1, the height of length of this node will be 2, this node will be 2. So the height of this one is 1, and which is 2 minus 1 is 1. So it is complete binary tree. And another criteria that we should consider is when we are constructing the tree, the nodes should be filled from left to right. So 1, then 2, 3, then for this node we should start, if there are some nodes to be added into the tree, we should start from the leftmost node. From this node we should start, then adding the other nodes, and once we added 2 nodes under this one, then we move to this one and we add only 1, because the only one node is left to be added into the tree. So we should just add that node from left to right. So for example, if we wrongly changed the node under this node, if we just change it to the right wing, so this will be wrong. This will not be considered as a complete binary tree, because the adding or connecting node should be then from left to right. And another very important tree is binary search tree, and it is an ordered binary tree. It is an ordered binary tree. Is a type of binary tree, but it is an ordered binary tree. So a binary tree that may be empty, this binary tree can also be empty, but here if it is not empty, it satisfies the following conditions. The first one, every node has a key and no 2 elements have the same key. So if one key is assigned, one key or any key attribute is attached to each node of the tree, so any 2 elements or 2 or more elements have the same key, so the key should be unique. And the keys in the right subtree are larger than the keys in the root tree. So when we are assigning keys to the nodes of the tree, we should assign keys that are larger than the root to be assigned for the nodes on the right wing, and the keys that are less than the root to be assigned to the left subtree nodes. And the left and right subtrees are binary search trees too. So those should be the conditions that we should consider when we are constructing a binary search tree. So for implementing the tree, for implementing a binary tree in a computer system, we use the structure concept and a pointer concept. So each node of a tree representing data points. So in order to store data items or data points in a computer system, we use a structure concept and pointer concept. So here we are just declaring a structure, self-referential structure, having one data part and a pointer part. So here, for example, we have a node as the node of the tree, representing the node of tree, and having the one data part. This one is data part, so this part is the pointer part, that is used for creating the link, between nodes, so for creating link between nodes we use the pointers. So as okay, so here, as the binary tree is the one having left and right nodes, we use two pointers, and the root node is initialized with null value, because a binary search tree, especially the binary search tree, can be left empty, so until we start adding nodes to the tree, initially we can set the tree as a null tree. So what operations that we can apply on binary search tree are the insert operation, the delete operation, the traversal operations, and then the update operation, the search operation. So the different operations can be applied on binary search tree. So when we are creating a binary search tree, the insertion operation can be used for inserting nodes into a binary search tree. So when we are inserting, for example, we can consider some cases. Case 1, if there is no data in the tree, that is, the tree is empty. So if the tree is empty and we have a node to be added into the tree, we just simply put the root node pointer to point to that particular node. Let's say we have a node 17 to be added into an empty binary search tree. So here, as this binary search tree is an empty tree, so here we can make that tree node to be pointed by the root node pointer to indicate that it is the first. So we have, so the first case is the case where there is no node in the tree, so the root node is pointing to the empty node. So if we have a node 17 to be added into the tree in which there is no any node in the tree, we can simply make the root node to point to that new node. And the case 2 is if there is data in the tree, already there are some nodes in the tree. So here we should search the appropriate position into which we can add that new node, and then inserting, once we identify the appropriate position, then we insert the node in that position. So for example, if we have a tree already filled with those nodes, and we have 17, so we should look for an appropriate node. So how we can search for nodes, how we can so if we have a node 17 to be added into already existed tree, binary search tree, we should compare how we can search for that position, for the specific or the appropriate position of the node. Is first we should start comparing the key of the new node with the root. So it is 17 and the root node key is 10. It is greater than 10. So as per the definition of the binary search tree, the key 17 is greater than key 10, so we should move to the right wing, so then we reach it at 15, so it is still greater than, so we should take the right wing. It is less than, so we should take the left wing. It is greater than, so we should take the right wing of 16. So the right wing of 16, it is added. So in this way we can add when a new node into the binary search tree by searching for its appropriate position, the appropriate position. So it is just simply made by calling the function insert binary search tree, so we can implement that function like this. So taking the binary, the node to be inserted, and the root node of the tree as the parent. So the root node of the tree and the binary, the new node to be inserted into the tree as a parameter, then comparing while inserted is equal to 0. That means this condition is, this variable is used for indicating whether the node is inserted or not. If not inserted, we should continue searching for the position of the node. If inserted, then we should exit from that loop. So if a root node pointer of the node value, the value of the node at the root right, that the root node pointer is greater than the node to be inserted. That means the node to be inserted is less than the root node, so we should take the left wing. So if the the root node pointer of the the root node at the left side is null value, we should add that node at that particular left wing of the node, and then assign inserted the value 1, indicating that the node is already added to the tree. Else, if not, we should change the root node value. That is, we should let the subtree to be the root of the subtree to be searched. So the root node should be changed to be the left root node, the node on the left of the root node. So we should assign the node on the left side to be the root. So this subtree will be searched as a normal complete tree. So it will then take it as a parameter, take it as a parameter, and then continue searching the appropriate. So it then moves to, if the right is null, if this condition is false, that is, it should move to the right side. Then if it is right side is null value, it should then add the new node on the right wing of the node. Then if this condition is false, it changes the root node subtree. So in that way the condition will be continued. Condition will be continued. So using the looping statement, it will continue looking for the appropriate position, and once the appropriate position is identified, it then adds the new node. And the other operations, the other operation is traversing the tree. And basically we do have those three traversal operations: the pre-order traversal, the in-order traversal, and the post-order traversal. So the pre-order traversal is just applied on the tree by taking first the parent, taking the left and the right wing. So we should traverse the tree in this way. We should traverse the tree in this way. So the tree is traversed in parent, left, right. And for this one we have the left in order. For left, parent, then right. For the post order, left, right, then finally parent. Finally parent. So here so the pre-order, when we are performing the pre-order traversal, so we should take, that is, traversal means displaying the keys or the contents of the nodes of the tree. So when we are traversing or displaying the contents of the tree in pre-order traversal, we should consider the parent first. So here the pre-order will display first 10, then one is left, it is 6, it is parent, so we should display. Then left, it is not a parent, is not a parent. So then we display after, from parent we should move to the left and then parent. So at the left side we don't have any node under 4, so we can just consider displaying this 4. Then after 4 we then take the right, because after left we should take right of 6, because we moved from 6 to left, that is to 4 we displayed. Then we take we finish it just taking the wing of left wing of 6, so now we can take the right wing of 6. Then when we are moving to the right wing of 6, we reach it at 8, which is parent, so we should display the parent, and then take the left side 7, display. Then right wing, there is no right wing, so we just move to the right wing of 10. The right wing of 10 is 15, so we should display this one. And we should take left, then 14, take left, then 12, take left, then 11, then take right, it is 13, no right. Now we can take the right wing, 18, then left, 16, then left, no left, then right, 17, then right, 19. Then finally we have this list. So in pre-order, this traversal is depending on the terminology, is depending on the position where we should display the parent value. Look, for pre, that is, the parent should be displayed first. For in, the parent should be displayed between left and right. Between left and right, it is between left, parent, right. That's why it is termed as in order traversal. And post order, that is, parent value will be displayed after we displayed left and right nodes. So this is why it is termed as post order. So for in order, look, for in order, if we traverse this tree using in order traversal, here we can take first this is a parent in order. This is a parent. No. Move to the left first to the left. Again, this is a parent because it is containing node under node 4 as a child. So we should take the left. So 4 is displayed. Then after left we display, then we display parent. Move to the parent. Then to the right. Then to the right. This one is parent. So before displaying the parent, we should take the left. That is 7. Then after the left is displayed, then move to the parent in order. Then parent 8 is displayed, then move to the right. There is no right. So we can now take the parent, that is 10, because left part is finished. So we can take 10. Then move to the right part. The right part, this one is parent, so parent should not be displayed here. So we should take left. This one is parent, we should take left. This one is parent, we should take left. So 11 is displayed. Then we should display now the parent 12. Then we can move to the right, that is 13. Then we can move to the parent 14. Then the right, there is no right wing. So now we can take the parent 15. Then move to the right wing. This is parent. We should leave this one for a while, then move to the left. This one is parent, having the right wing node. So there is no left, so we can display the parent 16. Then display 17. Then now we can move back to 18. Then display the right wing 19. So this is how we can display, or we can display the contents of nodes in order traversal. In post order traversal, we should display first left, then right, then finally the parent. So to traverse these three, in post order traversal, we should start from the root. So this is parent, should not be displayed. Then we should take left. This is also parent. We should stop. We should jump this one. Take left. Yes, this one is not a parent, so we can display this one. We can display 4. Then we can display. We take the 4, which is the left, so we should display. Then after displaying 4, we should take the right wing, because the parent 6 should be displayed after the right wing is displayed. So when we move to the right wing, this one is parent, so we should take the left side. So 4 should be displayed. Then we should take the right wing of 8, but there is no right wing node, so we can now display 8. Then now we can display 6. Then before displaying 10, we should take the right wing, because 10 is the parent of 6 and 15. So we should just jumping 10, displaying, just leaving displaying 10 and moving to the right wing. So this is a parent, so we should just leave this one, and we should take the left side. This is also parent. This one is the left, so it is also parent, so we should take the left side. So 11. Then the right wing 13. Then lastly the parent 12. 13, 12. Now the right part, no right part. Now we can take the parent 14. Now we can take the right part. It is also parent. We can take left. This is also parent. We can take left, but there is no left wing under 16. So we can take 17. Then we can move back to 16. Then we can move to the right wing, which is 19. Then back to 18. Then back to 15. Then back to 10. So finally 10 can be displayed. 10 can be displayed. So those are the 3 traversal operations that we can apply on binary search tree in order to display the contents of each node of the tree. The application of this binary tree can be used, or this binary tree can be applied in different areas. For example, the pre-order traversal, we can use this traversal operation for generating the mathematical infix expression. Prefix expression, sorry. The mathematical prefix expression. Then the in-order traversal for generating mathematical infix expression. So the post-order for postfix notation. So for mathematical postfix expression, we can apply post-order traversal. So first we need to have tree, binary search tree. For example, for this expression, for a given expression, this expression is the one that is just represented as a minus like b times c plus d plus e over f. This is a mathematical expression that is expressed or represented by this binary tree. So once we in order to represent, if we are given such expression, and we are asked to construct the binary search tree for a given mathematical expression, we should consider operator precedence level. And in operator precedence, consider once we can construct, consider the operator precedence level. So the operator having the least precedence level will be considered as the root of the tree. So here the operators having the highest precedence will be evaluated, will be represented as an internal nodes at lower levels. So and another thing that we have to keep in our mind is when we are constructing the binary search tree for mathematical expressions, the operands, the operators are put in internal nodes, whereas the operands are put in terminal nodes of the tree. That's why, as you can observe on this tree, the operators are internal nodes. And operands are terminal nodes. A, B, C, D, E, F are terminal nodes, and are operands. And operators plus, minus, multiplication, addition, and division are the internal nodes of the tree. Now, once we constructed the binary search tree, because here plus can be evaluated, will be evaluated at the last. We will evaluate plus. So we can just represent the multiplication and division at the lower nodes as an internal nodes. So the middle one will be the root node. So under the root node we have the subtraction and multiplication. Subtraction will be evaluated next, so multiplication will be evaluated first. So that is why we are bringing the minus above the multiplication. So minus on this wing, left wing A, on the right wing it is having the multiplication, and for the multiplication right wing B, the left wing B, sorry, then the right wing C. And for the next addition, this one, the right wing of this addition is then addition, and its left wing is D, and the right wing is multiplication. Then for the multiplication, division, the right wing is division, and for the division left wing E, right wing is F. So once we constructed this tree, then we can traverse this tree, and we can have prefix notation using prefix, pre-order traversal, parent, left, right. So parent, left, right. So parent, addition, this also parent, subtraction, left A, then to the right this is parent, to the left B, then B, then right C. Then we finish this subtree, then again move to the right. This is parent, we can display, then left wing D, then right side, this is parent, we display the left wing E, then F. So this is prefix, so pre-order. When we apply pre-order traversal, we got this expression, and this expression is the prefix expression of this infix. So this one is infix expression, this one is an infix expression, and those are the prefix, infix, and postfix. So this one the pre-order. So pre-order traversal displays or generates the prefix, in order traversal generates infix expression, and post-order traversal generates postfix notation. So those are the implementations of the three traversal operations. So the pre-order, the in-order, and post-order. So taking one node as parameter, and this is the current node. So every time we are just passing a node as a parameter to each of those functions, and those functions are recursive functions. So those are recursive functions, passing the current node to itself. So until they reach at the terminal node, and totally the node is the tree is traversed, it continues displaying the content of each node. So each of those traversal operations are implemented in this way. Operations on binary search tree. Another operation is searching the binary search tree, and this is very simple concept, just looking for one specific node. So given the value of the specific node and the root node of the tree, we can start searching for the tree. And still this binary search tree searching operation is also a recursive function, which is taking the node of the tree and the key of the node to be searched from the tree. So if the parent node value is equal to null, that is the tree is null value, so there is no need to perform search operation. And if the root node pointer num is equal to x, that is the value is obtained, so we can return true that the node is existed in the tree. Else, if the root node value num value is greater than x, so that means we should move to the left side of the tree to look for the required node, else we should move to the right node of the tree and look for the required node. So this is doing the same thing, so those are the same tasks that should be performed. That's why the function is defined as a recursive function, So rather than displaying the tree, simply the tree is, the node is obtained, sometimes we may just return, even we can return the value, the obtained value. So in place of just saying the root, the node is obtained, we can display the node itself, return the root node pointer, So it is just, this is a variable or the parameter that is that will hold the obtained value, value. So rather than simply returning this true, it is possible to return the value itself, we can also remove a node from the tree. So applying the delete operation, so it is after removal of a node from the tree, we should keep the conditions of binary search tree. So that's why we should carefully apply delete operation. So that after delete operation, the binary search tree can keep the conditions of binary search tree. So for example, if we consider this tree for applying the delete operation. So the case 1, if the delete operation is applied on the tree to remove node 7, that is deleting a leaf node or the terminal node, that is having no child. So we can simply remove, because if we remove this child, the resultant tree will not be affected, will not violate the binary search tree requirements. So after the removal of 7, we will have just a tree without node 7. This is very simple. So removal of any terminal node will not affect the binary search tree. So we can directly remove the node. But if we are deleting a node that is having one child, what we can do here? For example, if we want to remove a node 2, we want to remove node 2. So it is having the left child. So what we can do is, after removal, we can remove 2 after we connected the 3 with 1. So if the deleted node is the left child of its parent, and the deleted node has only left child of only the left child of the deleted node is made the left child of the parent of the deleted node. That is the condition. So here, if we remove 2, this 1 is the left child of 2, so we can make this 1 as the left child of 3. So if we make such adjustment after the removal of the node 2, the resultant tree will not affect or violate the requirements of binary search tree, because 1 is less than 3 and 4 is greater than 4. 4 is greater than 3. So still this is binary search tree. So we should just consider. We can also remove by copying, and you should also think of how we can remove this 4. what if we want to remove 4? If we want to remove 4, we can just simply connect 3 with 5, removing, just similar to this one. This is a right wing node, so we should make the right wing node as the right node of the deleted node parent. So 5 will be connected to 3, and this will be removed under 3. We have 2 and 1. So possible. So if what if we have another condition? Okay, we will see. Okay, deleting by copying. So deletion by copying can also be done. So what is this mean? Deletion by copying is the node to be deleted. First, we should copy the node to be deleted. The node to be, the child of the node to be deleted onto the part of the node to be deleted first. So 1 will be copied to 2, and now we can remove 1. So in this way we can make an adjustment on the tree. So 2 is overwritten by 1, and removing the the node which stored the key 1 will be possible. So making such adjustment on the tree will put the resultant tree in a state which is not violating the requirements of the binary search tree. Deleting a node having two children. How we can remove? So those are the conditions that we can consider. But here let's visualize the removal of a node having two children. Let's say 6. So if 6 is to be removed, first, before removal of node 6, first we should connect 3, the left wing, to B. We should look for first we should connect the right wing of the node to be deleted to be the right wing of the parent of the deleted node. So making 8 as the right wing and looking for the minimum value from the right from the left wing of the subtree of the deleted right wing of the deleted node, and connecting the subtree as the left wing. So connecting 3 to 6, we can make such adjustment on the tree. So still the tree is not violating the binary search tree requirements, because 7 is greater than 3, so on the 3 is under the left of 7 possible. So we cannot, but if here possibly we can also make 3 the left of 10, but here when we are making the 3 to the left of 10, this subtree should be connected to a node having the highest key value. This is 5. So from 1 and 2, 5 and 1 and 5 is having the highest value. So to the highest of right wing of the highest node, the disconnected node will be, the subtree will be connected. So we can connect a to the 5, and this way alternatively we can delete node 6. What if we want to delete 14? What if we want to remove 14? So what we can do? We can do just this one 12 to be the left, to be the left of, we can make to be the left of this one, I mean the right of 10. We can possibly make the right of 12 to the right of 10, and 18 will be connected to the right of 13. To the right of 13 we can put, or we can put 12, I mean 18 to the right of 10, and 12 will be added to the minimum node, which is 15, to the left of 15. To the left of 15 we can connect. By copying is also possible. We can possibly made by copying, and when we are removing a node with two children by copying, we should look for the largest element in the left side, and copying that one. For example, the left of 6, on the left of 6 the largest element is 5, so the largest terminal element, so 5 will be copied to 6, and we can remove node 5 this way. Or if we are looking for the right, if we are looking from the right wing, we should look for the smallest. For this one, for the smallest, that is 7 will be copied to 6. 7 will be copied to 6, and we can remove 7. We can remove 7. What about 14? How we can remove 14? How we can remove 14? We can look for by copying from the left wing for the largest, so 13 will be moved here, and we can remove the node of 13. Or from the right wing we can look for the maximum. For the maximum, I mean the smallest one. For this, from this one, the smallest one. So we can copy 15 to 14, then we can remove the 15 part. 15 node can be removed. So we can apply the copying, I mean delete operation by copying. What if we want to remove the root node? Removing the root node. So the removal of the root node, if the tree has only one node, that the root pointer will be left blank or left empty or made null value. If the root node has left child, the root node pointer is made to point to the left child, and the right child of the root node is made the right child of the node containing the largest element in the left of the root node. Look, for example, if we want to remove the root 10 here, we can remove 10, but here what adjustment we can do is we can consider 6 as a root node, and this disconnected part, disconnected subtree, this disconnected subtree to be connected to 9, to be connected to 9. So we should look for the largest node. We should look for the largest node, and from the left wing, and then connect the right wing of this deleted node as the right wing of 9, the largest node. If we want to make 14 as the root of the tree, we can take root 14 and this disconnected subtree to be connected to the smallest value, which is 11. So smallest is 11, so we should connect to the smallest wing, I mean left wing of the smallest node. So in that way we can delete the root node. We can also remove a node by copying. we can also remove a node by copying. So when we are removing a node by copying, we can just look for smallest, I mean the largest node from the left wing, and just make copy that largest node to the root node and removing the copied node. Or we can just look for the smallest. When we are looking for the node from the right wing, we should look for the smallest. And for the smallest, for example, we can consider 11. 11 can be copied to 10, and we can remove 11. So in that way we can remove the node, root node. So those are the functions, the delete operation function, delete operation by copying. So those are the implementations. So you can go through those definitions of the delete operation, and you can implement. That's all. Thank you.